Hi, everybody. Dr. White here with a study of how the definite integral can actually represent the net change in a quantity if you're integrating over the rate of change in that quantity. So we've really touched on this idea before, and we've even used it a little bit, but this is the part of the book where they really trot it out and make it explicit, give you more examples. So think about this. The old distance equals rate times time formula from high school. I'm going to think of distance here instead of distance. I'm going to think of displacement, change in your position. Okay, it's really saying this formula is really saying that the displacement is the velocity you have times how long you've been traveling at that velocity delta t. Okay, and if you think of it graphically, like a time axis here and a velocity axis for your vertical, and say for some little interval of time, delta t seconds maybe, you travel at some one constant velocity, say v of t is constant over that time interval, then the displacement is going to be v of t times delta t, and it's the area of this rectangle, okay? And we know that the definite integral of a function from an upper to a lower bound is a signed area, which is a limit of Riemann sums of areas of rectangles like this. So thinking to the fundamental theorem, part one, where the signed area from A to B under little f of x is the difference from A to B of any of its antiderivatives, capital F, think about what if little f was velocity. Capital F, position, is one of the antiderivatives of little f, And I like to think sometimes of position as, and the book likes it too, think of position as a function little s. Then what this theorem really comes to is that the integral from A to B of velocity is the difference in positions. So that is to say, your displacement, the net change in your position from time A to time B, is the integral of the rate of change of your position. This goes for any rate of change at all, for any type of quantity, not just for like velocity being rate of change of position. It goes for any type of rate of change. Let S be any quantity at all that could have a derivative, a rate of change. The amount it changes from one time to another time, from time t1 to time t2, this difference here, is just the integral from the t1 to t2 of its rate of change function. So this is what the section calls the net change as the integral of a rate of change theorem. But it's really just the fundamental theorem of calculus, part one. So a couple little examples. Let's say water flows into an empty reservoir at a rate of 3,000 plus 20 times t liters per hour, where t is how many hours you sit there and watch it, okay? So I guess it starts off empty at time 0, and then water comes in. And I guess as time goes on, it's coming in faster and faster because 3,000 plus 20t gets bigger and bigger. How much water is in the reservoir after 5 hours? So here's a way of thinking about it. Let's let Q of t be the quantity, the amount of water. Let Q of t be the number of liters of water in the reservoir after t hours. Then Q prime of t is this 3,000 plus 20t liters per hour of which they speak in the problem. And the net change theorem, the fundamental theorem of calculus if you like, says that Q of 5 minus Q of 0 would be the integral from 0 to 5 of Q prime of t dt. Now I want to find Q of 5, how much water is there after 5 hours. So I think to myself, I got to get this, and I'll worry about the q of 0 in a minute. Let me see if I can get this. Well, let's see. Q prime of t is 3,000 plus 20t. The antiderivative would be 3,000t plus 20 times t squared over 2, which is 10t squared, so that's an antiderivative. Evaluate between 0 and 5, and I end up with like 15,250 liters. So that's the difference here. If I add q of 0 to both sides, I have to get the q of 5 is that difference plus a q of 0. And then I remember, oh, they said the reservoir was empty when you started watching it. So q of 0 is actually 0. And so the difference is really the number that you wanted all along. You got to watch out when you want to find the quantity at an end time. Make sure you keep track and think about what the quantity was at the beginning time, because it's not always going to be 0. Hey, here's another problem. So we know that displacement is change in position. Velocity is rate of change of displacement. And so we know that displacement from time t1 to time 2 is this definite integral velocity. Displacement is different from distance, okay? Displacement is change of position. Distance is how far you really had to go as you possibly wind around. You know, like imagine you start somewhere and you just start walking around and you kind of walk around a bunch of circles and you come back exactly to where you were at the beginning. Your displacement, your change in position is actually 0. But it's not like you walked 0 feet. You might have walked quite far, even got tired, right? There's a difference between displacement from one time to another versus distance traveled from one time to another. And the book defines distance traveled from one time to another as the integral of the absolute value of your velocity. And you might wonder, like, why do they do that? And how could we get any more light on the difference between distance traveled versus displacement? So to get that light, let's work with an example, which is actually in the book. I'll just give you a little more detail on how they work it out. Suppose a particle moves along some straight line. Imagine just some horizontal line. And the particle starts somewhere on that line, and it starts moving along that line with some velocity, which may change, you know. And so it may move faster and faster or slower and slower. It may even back up. That would be like having negative velocity, you know. So say it moves along the line with velocity v of t equals t cubed minus 10t squared plus 24t meters per second. That's its velocity at any time t. Could we find its displacement from 0 to 6 seconds? How much did its position change in that time? So if we think of position as s of t, then s of 6 minus s of 0 would be the integral of the v of t. And so I just grab the antiderivative, and I evaluate between 0 and 6. And if you pull out a calculator and work with it, you'll get 36. And it's 36 meters because the velocity was meters per second and the time was measured in seconds. But how about the distance traveled? What would be the integral of the absolute value of v of t dt? Well, you can't just like go and whip out this antiderivative, because you're not looking at v of t here, you're looking at the absolute value of v of t. And there is no quick and easy formula for the integral of the absolute value of anything. But instead, there's an approach that we've worked with before. What we're going to need to do is going to need to break up this integral into parts. Parts where v of t is positive and parts where it's negative. And then we can deal with the absolute value. So let me first think, like, when is this v of t positive and when is it negative? I start by thinking, when is it 0? And so I got an equation to solve, and I see I can factor out a t. And then I see I can factor this to this. And so I think, okay, for what t's is this 0? Well, t could be 0, it could be 4, it could be 6. And then I head over and do a little analysis on each of those factors, the t minus 4, and the t minus 6. And I write a real number line down for each factor. So there's the real number line for t, and here's the real number line for t minus 4, and here's the real number line for t minus 6. And I decorate each real number line with the zeros for v of t. So the places where v of t was 0, 0, 4, and 6, I just stick those on each of these number lines. And notice how I've written the number lines down so that they're right under each other. The numbers are lined up. That's going to be helpful. And then I think about t, and I think about where's it positive, where's it negative? Well, before 0, it's negative. But after 0, it's going to be positive, both between 0 and 4, between 4 and 6, and after 6. How about t minus 4? Well, it's going to be negative before 4, positive after. How about t minus 6? Negative before 6, positive after. Now I think about the product. So I write a real number line down for the product, v of t. And I just analyze the product on each of the intervals that are determined by these 3 breakpoints, 0, 4, and 6. So how about for t's less than 0? Well, then I'm looking at the product of 3 negatives, which is a negative. How about between t's between 0 and 4? I'm looking at the product of a positive times a negative, that comes out positive. And similarly, this analyzes to a negative, and this analyzes to a positive. So now I know where v of t is positive and where it's negative. If I made a rough graph of v of t, I'd have to show it positive from 0 to 4, negative from 4 to 6, positive afterward, okay? And I am going to be taking the integral of the absolute value of v of t. And absolute values, you leave the number alone when it's positive, you take opposite when it's negative. So a rough graph of the absolute value of v of t would be like this. You just take this little hump here and make it exactly opposite. So now it's like a nice positive hump. And if I want the integral from 0 to 6 under this curve, I'm going to have to break at the 4. And so I'm looking at the absolute value integrated from 0 to 4 plus the absolute value integrated from 4 to 6. Now from 0 to 4, v of t was positive, so its absolute value is just v of t. From 4 to 6, the absolute value of v of t would be the opposite of v of t. Now I can fill in that I know what v of t is, and I get these two integrals. I can totally go and find their antiderivatives. I am fine. And so the first one, I just got my antiderivative. I go from 0 to 4. This next one, I'm working in the minus sign before I take my antiderivatives, and I end up with this. And I've got to evaluate between 4 and 6. So there's some, arithmetic to do, and the book shows you a little bit more of that arithmetic, I think. And you end up with 148 over 3, which simplifies down, if you like, to 49 1/3 meters. Okay, as compared to the 36 meters here. So it traveled more distance than it actually got in displacement. And the reason for that is because the velocity dipped negative for a while. From 0 to 4 seconds, the velocity was positive. The particle was actually traveling forward. But then from 4 to 6 seconds, it started traveling backwards. Traveling backwards cut down on the amount of actual displacement, but it did not cut down on distance. Even when you're going backward, that counts as positive distance that you're traveling. So take a look at the book's treatment of it and the extra pictures that they show, and I think you'll find it illuminating along with this coverage here. So that's enough practice for this section. I'll see you later if I can find out where to end. Here we go. Bye-bye.